Okay, let's quickly discuss the answers to a few worksheet problems and then we will discuss about the interference pattern. So second one, you are shown a wave, it is traveling to the right with a speed 20 centimeters per second. Okay. From the diagram, I think you can get its wavelength and all also. So quickly tell me, what is the wavelength of the wave? Like these are some important wave properties which you need to understand thoroughly to be able to explain the interference pattern and all, okay, on your own. What is the wavelength of the wave that you see on the screen? Isha, how much is the wavelength?
So 1 centimeter.
1 centimeter, that's all. Wavelength is the length of each pulse of the wave. So from here to here, you can say it is 1 centimeter, fine. And you know the speed, you know wavelength. How to calculate frequency? How are they related? What is the formula relating speed, wavelength, and
V is
frequency?
equal to lambda f.
V is equal to f lambda, so f becomes V by lambda. That's fine, you can get it. Next, okay, why it is important in this chapter also I will tell you. You may be asked questions where there are two non-coherent sources, okay, sources emitting waves at different frequencies. Then you need to understand the relation between frequency wavelength. Then you will be able to tell the phase difference with which they interfere at a particular point. And okay, in that case, we don't call it interference, we call it superposition. So you'll be able to tell the phase difference with which they superpose, and you'll be able to comment on intensity and all. Okay. So frequency f is equal to V divided by lambda. So basically in this chapter, they prove the wave nature of light. And to prove wave nature of light, they use interference. They check if light undergoes interference or not. Okay. So you will have cases where two or more waves are being superposed. So when multiple waves superpose with constant phase difference, you call that as interference. Okay. Next, phase difference between the points x is equal to 0 and x is equal to 4 centimeters. Look at the diagram and tell me quickly, what is the phase difference between this point and this point? See, every time the source completes one oscillation, one pulse will get generated. And every time the source completes one oscillation, the phase advances by 2 pi. Okay, because this is a sinusoidal wave. For a sinusoidal wave or for a sine function, the period of repetition is 2 pi. Okay, so every time one pulse is generated, the phase increases by 2 pi or advances by 2 pi, you can say. Now, the point x is equal to 0 and the point x is equal to 4, they are separated by 4 pulses, 4 wavelengths. Okay, every time one pulse is generated, means for every one wavelength, the phase difference is 2 pi. Okay, then for four wavelengths, the phase difference will be 8 pi. The relation between distance and phase difference is the most important thing you will use in this chapter. So when the distance between 2 points on a wave is one wavelength, the phase difference between those 2 points will be 2 pi. And because we take waves traveling with constant speed, okay, this ratio will remain fixed. So distance between 2 points divided by the phase difference between them will always be lambda divided by 2 pi. So based on distance, you can tell how much is the phase difference. Okay. Next, you are asked to identify any 2 points on the graph, okay, or on the wave, which have a phase difference of 5 pi. Now it's like from this idea that for each wavelength you have a phase difference 2 pi, you can easily identify 2 points which have a phase difference 5 pi. One wavelength corresponds to phase difference 2 pi. Two wavelengths, 4 pi. 2.5 wavelengths, 5 pi phase difference. So you just have to mark 2 points which are separated by 2.5 wavelengths. So you can take x is equal to 0 as one of them. Then 1 wavelength, 2 wavelengths, 2.5 wavelengths. This point. This point is 2.5 centimeters itself. So x is equal to 0 and x is equal to 2.5 are 2 points which are separated by a phase difference of 5 pi. In fact, you can find out infinite such pairs of points which are separated by a phase difference of 5 pi. Is this clear? Any doubt in this? Okay. Next, phase difference between the points x is equal to 2 and x is equal to 7.5. You'll use the same relation again. X is equal to 2 and x is equal to 7.5. Okay. The gap between them is 5.5 centimeters. So for a gap of 5.5 centimeters, you find out how much is the phase difference by taking wavelength as 1 centimeter. That's all. So 5.5 into 2 pi, 11 pi is the phase difference between them. So the important thing to remember from this problem is that 2 points separated by 1 wavelength will have a phase difference of 2 pi. Because 1 wavelength corresponds to 1 cycle of the sinusoidal, 1 cycle of the sine function. Next, question number 3. We know that for every distance of 1 wavelength, the phase difference between the 2 points on the same wave is 2 pi. Suppose phase of oscillation of a wave source is phi naught. What is the phase at a point which is at a distance of 3 lambda by 2 from it? Okay, let's use this diagram itself. Suppose this is the source of the waves. They're asking you, okay, they're saying that the phase of oscillation of the source is phi naught. Now, source will be oscillating up and down, no, producing the wave. So it could have its own phase of oscillation. It will have its own phase of oscillation. What is the phase at a point which is at a distance 3 lambda by 2 from it? Now, if you go to a distance of lambda, there should be a phase difference of 2 pi. So the phase at this point, okay, can be source phase minus 2 pi or source phase plus 2 pi. Okay. Yeah. So if you go to 3 lambda by 2, then it will be source phase minus 3 pi or source phase plus 3 pi. The phase difference will be 3 pi. Okay. So you can write phi naught plus or minus 3 pi. That will be the phase of oscillation at that point. Okay. Next question, just a moment. Next one I think is about 2 waves meeting at a particular point. Right. The picture below depicts 2 waves arriving at a common point from sources S1 and S2 which oscillate with the same frequency. Okay. See, if 2 waves are traveling in the same medium, they will definitely have the same speed. Okay, because wave speed depends on the medium. And if frequency is also equal, V is equal to F lambda, automatically wavelength will become equal. Okay, this idea is also important in this chapter. In YDSC, single slit diffraction and all, we usually assume there is vacuum between the slits and the screen. Okay. So speed of the waves will be same, and if sources are coherent, means they oscillate with same frequency or they produce light of the same frequency, then the wavelengths they produce also will be the same. But you may be asked problems where wave from one source is traveling through one medium till it reaches the screen. Okay, or you may be asked problems where there is a glass slab placed in front of one of the sources. Okay, so you need to understand how the medium influences things, and you need to understand that even if frequency is same, if the speeds are different, the wavelengths can be different. Okay, so for now we are assuming the medium is same, and if they oscillate with same frequency, obviously they produce same wavelength. The distances S1 to P and S2 to P are both equal to 5 lambda. Observe the diagram and answer the following. The phase difference between the sources. Okay, just look at what the sources are doing. The source S1 at this instant is producing a crest. The source S2 also at this instant is producing a crest. Therefore, they are oscillating in phase at this instant. And because the frequencies are same, they'll keep oscillating in phase with each other. Why? Because if frequency is same, time period is same. So see, after a short while, S1 will produce a trough. And at that time, exactly at that time, S2 will also produce a trough because the time periods are same. time period of oscillation. So they'll always oscillate in phase with each other. Okay, if they're in phase once, they'll always be in phase, provided they have the same frequency. Suppose frequency is different. That means time period will be different. Then if S1 goes to a state where it is producing a trough, because the time periods are different, it is possible that S2 may still not be producing a trough. So they can go out of phase if frequencies are not equal. Even if they are in phase at one instant, next instant they can go out of phase. They will go out of phase, in fact. Okay, so here they are oscillating in phase, then the phase difference between the sources, you can take 0, or any even multiple of pi can be taken. That is what we mean by being in phase. Next, the phase difference between the waves when they arrive at the point P is. Okay. Now, assume that two sources have 0 phase difference. Usually when two sources are in the same phase, no, we assume phase difference is 0. We don't take 2 pi and all. From S1, the point P is at a distance of 5 lambda. For every wavelength lambda, for every distance lambda, you get a phase difference of 2 pi. Means the phase of S1 difference the phase at the point P due to the first wave. Okay. I'll call it as phase at P due to 1. Okay, 5P1. This difference should be, for every wavelength, if it is 2 pi, then this difference should be 10 pi. Okay, so the phase difference between S1 and the point P for that black wave is 10 pi. Similarly, phase difference between S2 and the point P due to the second wave is also 10 pi. Now, these two are equal. The sources are in phase with each other. The right-hand side is also equal. That means these two should be equal. Okay, so the phase of the wave arriving at point P from S1 and the phase of the wave arriving at point P from S2, these two are equal. So what's the phase difference when they arrive at point P? The answer is 0 again. Okay, they arrive there at the same phase. And you can see in the diagram also, the crest from S1 has arrived there. At the same time, the crest from S2 has also arrived there. Just a moment. Okay, next question. Okay. Consider two sources S1 and S2 emitting waves of equal wavelength and one wave each from S1 and S2 reaching a common point P as indicated in the diagram below. Like if you had studied YDSE before, then you will know why this matters, because in YDSE this is what happens. Okay. Two sources emitting waves, and from each source one wave will be reaching a point on the screen. Okay. So S1 to P, the distance is 7 lambda, as you can see. S2 to P, the distance is 6.5 lambda. Okay. Now the sources are emitting waves of the same wavelength, means they have the same frequency. Okay. If the phase of oscillation of the source S1 is phi, okay, then what is the phase of oscillation at point P of the wave produced by S1? Can one of you answer this quickly? Source phase is phi, and we know that there is a wave going from that source to the point P. So what will be the phase at point P is the question. Okay, I got one answer as 7 by 2. It's not 7 by 2, it is 7 into 2 pi. Okay. For every distance of lambda, the phase changes by 2 pi. Okay, so if there's a distance of 7 lambda, then the phase changes by 7 times of 2 pi, that is 14 pi. So the phase here at point P due to the first wave, you can take as phi minus 14 pi. Okay, why I'm taking minus is because, see, the wave is going this way. When the wave just arrives at P, the source would have completed 7 oscillations extra. Okay, so the source phase will be ahead, point P's phase will be behind. Okay, or P is lagging, I can say, because 7 extra pulses have been emitted by the source which have not arrived at P yet. Okay, so P has done 7 oscillations less than the source. That's why I'm taking 5 minus 14 pi. Okay, lesser phase. Not an issue. Next, if the phase of oscillation of S2 is phi, okay, the two sources are in phase. So this phase also I'm taking as phi itself. Then what is the phase of oscillation at point P produced by wave coming from S2? Same logic you will use again. For every wavelength, the phase difference is 2 pi. Now, the distance from S2 to P is 6.5 wavelengths. So the phase there will be 5 minus 6.5 into 2 pi, that is 13 pi. Okay, so the wave coming from S1 and the wave coming from S2, they arrive at point P with different phases, means they arrive there with a phase difference. Even though, like in this case, the sources were in the same phase. You can see S1 has just produced a crest, S2 also has just produced a crest. They are oscillating in the same phase. But when waves from those sources arrive at a common point, they arrive with a phase difference because they traveled different distances. Okay. As seen from the diagram, how much is the phase difference between S1 and S2? Between S1 and S2, the phase difference is 0. Okay, in the diagram, you can see they are oscillating in phase with each other. Then derive the phase difference with which they arrive at point P. The phase difference with which they arrive at point P, just subtract these two, they arrive with a phase difference of pi. Okay. And in terms of interference, if you want to talk, if waves reach a common point with a phase difference of pi, that means the crest of one wave arriving at that point when the trough from another wave is arriving. Okay. Phase difference of pi means what? They are exactly out of phase with each other. So when one wave's positive extreme is reaching there, another wave's negative extreme is reaching. Then what kind of interference is this called? If two waves interfere completely out of phase with each other, what kind of interference is it called? There are two extreme cases of interference, constructive, destructive. Okay. Constructive is when the waves interfere in phase with each other. Okay, that means when they have a phase difference of 0 or 2 pi, 4 pi, and so on, in that case, the interference is called constructive. In this case, it will be destructive, okay, because they interfere exactly out of phase. Now, why does all this matter for this chapter? Waves from two sources, when they arrive at a point, see, when single wave arrives, it's like energy reaches that point and you can feel that energy also. Like suppose these are sound waves. Let's say there is one sound wave coming from S1 to the point P. If that is the only wave arriving at point P, we can hear the sound. Okay, those compressions and rarefactions, they'll oscillate our, what is that thing which oscillates inside the ear? Eardrum. Yeah, they'll oscillate the eardrum, we'll be able to hear the sound. Suppose the sound only from S2 reaches the point P and you are there at point P, you will be able to hear that sound from S2 also. Okay. But if both S1 and S2 produce sounds and they arrive at the point P at the same time, you will not be able to hear anything. Okay. There are two sources of sound, but you don't hear anything. That is possible because the sound from one source is cancelling the sound from another source. Okay. That possibility is also there. And that is what happens in noise cancellation in earphones. Okay, so technically what the noise cancelling earphones do is they sense or they detect sound from the surroundings. Okay, suppose you are in a traffic jam. Okay, there are a lot of horns that you can hear. So the noise cancelling earphone, it will hear that sound. Okay, it can receive that sound, obviously. When your ear can receive, the earphone also can receive if it is designed to do that. And what it immediately does is produces a, what can I say, a counter wave to that. Okay, the sound from the surroundings, okay, let's say from an adjacent car horn or something, is about to enter into your ear. But the earphone will receive the sound before it enters into your ear. The moment the earphone receives the sound, it produces an opposite wave. Okay, an inverted wave, you can say, or a wave which is exactly out of phase with the incoming sound. Then both waves will enter into your ear. Okay, the horn sound will anyway reach your ear. It will pass through the earphone and reach your ear. And at the same time, the sound produced by or the wave produced by the earphone also will enter into your ear. Okay, so one wave, the original wave is entering, another wave which is exactly out of phase with it is also entering. As a result, you don't hear the external sounds. Okay, so that is how noise cancellation works. And in Young's double slit experiment, this scientist Young, he uses this same idea to check if light also shows this behavior, because any wave should show this behavior of interference, constructive, destructive, and all. If that happens, that is proof that the thing has wave nature. Okay, sound has wave nature because you can see that it undergoes interference. Okay, you see water waves on the surface of water also undergoing interference. Any wave should undergo interference. So that is the idea that Young used to check if light has wave nature or not. Anyway, so if they arrive at a common point with a phase difference of pi, 3 pi, 5 pi, any odd multiple of pi, then they undergo destructive interference. And in destructive interference, in case their amplitudes are equal, okay, let's say amplitude of this wave is A1 or A, okay, and the amplitude of this wave is also A, then if they undergo destructive interference, effective amplitude becomes 0. And if effective amplitude is 0, effective intensity will be 0. You will not hear anything. If it's a light wave, you will not see anything. Okay. So two sounds can cancel. Similarly, two lights also can cancel if light is a wave. And yes, light is a wave. It is proven now. The previous problem, we saw that the waves arrive at the point P with phase difference 0. If they arrive at point P with phase difference 0, that is called constructive interference. Okay. So effectively what happens, you can see here, when the crest from the source S2 is arriving, the crest from the source S1 is also arriving there. Means two positive extremes are arriving at the same time. Now S1, let's say S1 has just produced a compression. Okay. In a sound wave, when we show sound waves are actually longitudinal waves, but when we draw a sinusoidal wave like this to represent sound wave, it means we are showing pressure variations. Okay. High pressure means compression, low pressure means rarefaction. So crests have reached means two compressions have reached from S1 and S2. So both the compressions will add up. Okay, that is what we call as constructive interference and create a much stronger compression. Okay, so you will hear a much louder sound if two sounds from two sources undergo constructive interference. Okay. Same with light also. If lights from two sources undergo constructive interference, you will see a much brighter spot there. Okay. For in terms of sound waves, the you can feel intensity in terms of loudness. Okay. For light waves, the intensity is felt in terms of brightness. Next, question number 6. Just a moment. Okay. There are two waves from sources S1 and S2 arriving at a common point P, as you can see. S1 to P, the distance is 5 lambda. S2 to P also, the distance is 5 lambda. Okay. So equal distances. But okay, let's see the question. The distance from S1 to P, S2 to P is 5, where lambda is the common wavelength of waves emitted by both sources. First question, if the phase of the source S1 is phi 1, okay, S1 has its phase as phi 1, then the phase of oscillation at P due to the wave from S1, okay, this is easy only. S1 to P, the distance is 5 lambda. For each lambda, the phase varies by 2 pi. So the phase at P due to S1 will be phi 1 minus 5 times of 2 pi, that is 10 pi. Okay. Next, same question with S2, but S2's phase is phi 2. Then the phase arriving there, the phase of the wave arriving there from S2 will be phi 2 minus 10 pi. Okay. If the phase of the source S1 is phi 1 and the phase of the source S2 is phi 2, the phase difference between the sources is? That is a simple question. The phase difference between these two will be phi 1 minus phi 2, or phi 1 difference phi 2, you can say. Whichever is greater, you will take first. That's the phase difference between the sources. You can see from the diagram also. S1 has just completed producing a crest. Next, it will produce a trough. Okay, but S2 is still producing the crest. Okay, so they have a phase difference. They're not exactly doing the same thing. And you see the waves that have arrived at point P also. From S2, the crest has just arrived. From S1, the crest has passed the point P. Okay, if you visualize properly, the crest has passed the point P. So they are arriving at point P also with some phase difference. They're not doing the exact same thing when they arrive there. In fact, from S1, the mean position has arrived there. Okay, crest is positive extreme, trough is negative extreme, mean position is the mean value, okay, or the average position. Fine. So phase difference between sources, this part is done. Fourth question. If the phase of source is S1, phase of source is S2, then the phase difference between the waves arriving at point P. Okay. We know with what phase each wave arrives there. Then the phase difference with which they arrive there, subtract these two, it will again be phi 1 difference, phi 2. Because the distances from the sources are equal, whatever is the phase difference between sources, you will see the same phase difference appearing at the point P. And this is also important in to answer problems based on YDSC and all. Yeah, Pradyun, that is okay. Yeah. This is also important to answer problems based on YDSC because you may be asked questions where there is a slight phase difference between the sources and you have to find out what happens to the interference pattern. Okay. So you need to understand if sources have a phase difference, then how will they arrive at point P? With how much phase difference will they arrive at a particular point on the screen? Based on that, you will answer what happens there, constructive interference or destructive interference and so on. Then, okay, fine. This is all we discussed. Try to answer this question. Suppose there's a source S1 here and a source S2 here. Let's say there is a point P which is equidistant from S1 and S2. So S1P is equal to S2P. Okay, wait, equidistant we have just discussed. Let's assume there is some difference in the distance. Take some point P here. From S1 to P, let's say the distance is let's take 3.5 wavelengths, and from S2 to P, let's say the distance is 4 wavelengths. Okay. Let's say S1 has a phase of its own phase is phi 1. Then Isha, tell me, what will be the phase of the wave arriving at point P from S1 if the distance is 3.5 lambda? Correct. So phase difference of the source minus 7 pi. For every lambda, you have 2 pi. Okay. So phi 1 minus 7 pi. What about the phase of the wave arriving there from S2? Suppose S2's own phase is phi 2. Okay, based on that.
Phi 2 minus 8 pi.
Okay, 4 wavelengths, so 8 pi. Then what is the difference in phase between the waves arriving from S1 and S2? Just subtract these two.
Yes, sir. Pi 1 minus pi 2.
Phi 1, okay, you can take phi 1 minus 7 pi, that is the phase of one wave, minus of phi 2 minus 8 pi. So it will be phi 1 minus phi 2 plus pi.
Plus pi.
Okay, right. And we can generalize this also. Instead of 3.5 lambda, suppose this distance is given x1. And instead of 4 lambda, let's say this is given x2. Now you tell me, what is the phase with which the wave arrives there from S1? If the distance is x1.
Pi1 minus 2x1. 2x1 pi.
No. X1 is not the number of wavelengths. No, it's the actual distance. If there is one wavelength, 2 pi, two wavelengths, 2 into 2 pi, n wavelengths, 2 into n pi. Now you are saying 2 into x1 pi. X1 is not the number of wavelengths. It's the actual distance.
Okay.
What's the relation between distance and phase difference?
X1 by 2 pi.
No. Okay. Suppose wavelength is 10 centimeters and there is a distance of 50 centimeters. Then how many wavelengths does it correspond to? If wavelength is 10 centimeters, then how many wavelengths are there in a distance of 50 centimeters?
5.
5 wavelengths. Okay. So number of wavelengths is distance divided by the wavelength. So similarly here you can tell how many wavelengths are there. Number of wavelengths will be lambda divided by x1. Wait, x1 divided by lambda. Okay. Then you can tell what is the phase difference. For each wavelength, the phase difference is 2 pi. Then for these many wavelengths, it will be this many into 2 pi. So phi1 minus x1 by lambda into 2 pi. Okay. That's the phase difference with which the waves arrive from S1 at P. Okay. Or that's the phase with which the wave arrives from S1 to P. Is this clear?
Yes, sir.
Similarly, you can tell the phase with which the waves arrives from S2, phi2 minus x2 by lambda into 2 pi. And you subtract them, you will get the phase difference with which two waves arrive at the point P. This is the phase of the first wave. This is the phase of the second wave. Then the phase difference at point P will be, you need to subtract these two, phi1 minus phi2 minus of x1 by lambda into 2 pi minus x2 by lambda into 2 pi. Anyway, see, don't think of these as formulas. Just remember the idea. So if you know the phase difference between the sources, okay, phase difference between sources is known, and you know the difference in distances, x1 and x2, okay, or x1 minus x2, then you can tell the phase difference with which the waves arrive at point P. This idea will help you solve even tough questions based on YDSC. Okay. Sources having different phase, some random point on the screen, different distances from the sources, you can still tell what happens there, constructive interference or destructive interference, or what exact intensity you will get there, you will be able to answer. Okay. Fine. So, right, these are the ideas that you need to know. Next is the actual experiment that was done to prove the wave nature of light. Okay. So Young had this idea that if light is a wave, then it should show interference. But how to check whether it is showing interference or not? So the idea was this. The idea was to take 2 point sources of light. Okay. Let's call the sources as S1 and S2. With a small separation between them, of course. Let's say the separation between the sources is D. Okay. And at a certain distance from the sources, they placed a screen. Okay, why? You have to see light undergoing interference, no? So to see the pattern, you will need a screen. Screen will have to be white, of course, not black. On or okay, shall we use black? Just a moment. Just to understand things better, let us draw it properly. Consider two sources S1, S2 which are coherent. What does coherent sources mean? Coherent means they have the same frequency. Okay, and if frequency is same and the medium in which they are present is same, then they'll produce waves of the same wavelength. Okay, remember this term coherent, it's important. Okay. And at a certain distance from the sources, they place a screen on which they expect to see the interference pattern. Okay. The distance from the line joining the sources to the screen, let's call it capital D. Okay. Now, the screen is parallel to the line joining the two sources. Therefore, this point, which is which lies on that perpendicular bisector of the sources, will be a point which is equidistant from the two sources. So S1 to O and S2 to O, the distance is same. Fine. Now, suppose S1, S2 are two sources which are in phase with each other. Okay, this is an assumption that we are making. Suppose S1 and S2 oscillate in phase. Okay, means when S1 produces a crest, S2 also produces a crest and so on. The distance from S1 to O, okay, and the distance from S2 to O are the same. Then the wave arriving at O from S1, which travels this way, let's say it travels a certain distance x1, and the wave arriving at O from S2 also travels the same distance. Then Isha, you tell me from what we just discussed, will they arrive there with any phase difference or will they arrive there in the same phase? The sources are in phase. The waves coming to the point O, will they come in phase or will they arrive with a phase difference?
In phase.
They'll arrive there in phase with each other, correct? Because the distances are same.
Yes.
So in terms of what we just discussed, if you want to answer, let's say the sources have a common phase of phi, and this distance is x, this distance is also x. Okay. Then the wave arriving here from the source S1 will have a phase of phi minus x by lambda into 2 pi. And the wave arriving there from the source S2 will have a phase of phi minus x by lambda into 2 pi. They arrive there with the same phase. So the phase difference with which they arrive there becomes 0. Okay. And if two waves arrive at a common point with 0 phase difference, what kind of interference do they undergo?
Oh,
Constructive interference. So basically for the point at the point O, the path difference is 0. The waves have traveled the same distance. So the path difference is 0. And since sources are in phase with each other, the phase difference with which they arrive there is also 0, which means they undergo constructive interference. And if they undergo constructive interference, you will see maximum intensity at that point. So you will see a bright spot at this point O. Okay, we considered two sources of orange light. Okay, orange colored light. You could have taken red also, that's fine. Just on black, orange will be better seen. So if the sources emit orange light, then you will see a bright orange spot at the point O. Okay. Next, move away from the point O. Consider some other point on the screen. Let's say this point. definitely any point other than O will be at different distances from the sources. Okay, from S1 to P, the distance is different, and from S2 to P, the distance is different. And if distances are different, sources are oscillating in phase, then you can say for sure, okay, not just a possibility, you can say for sure that they will arrive there with a phase difference. Okay, consider a point P to which the distance from S1, okay, let's visualize waves arriving at P from S1 and S2. From S1 to the point P, let's say the distance is x1 this time. P is some random point on the screen. Let's say this distance is x1. And from there, from S2 to that point P also, there will be a wave going. And let's say the distance is x2. Sources are in phase. So the wave arriving at point P from the first source will have a phase of phi minus x1 by lambda into 2 pi. And the wave arriving there from second source will have a phase of phi minus x2 by lambda into 2 pi. So what is the phase difference with which they arrive at the point P? Subtract those two terms. You will see that it is x2 minus x1 divided by lambda into 2 pi. And x2 minus x1 is something we call as path difference. How much extra distance one wave has traveled compared to the other. Okay. So the phase difference with which they arrive at any random point on the screen is the path difference divided by wavelength multiplied with 2 pi. Is this clear?
Yes, sir.
Okay. Therefore, the path difference there, not path difference, sorry, the phase difference with which they arrive there is delta x divided by lambda into 2 pi. Okay. Now, as you keep going away from the point O, this path difference, the extra distance traveled by one wave compared to the other wave, will keep on changing. Okay. Now, up to what maximum value can it change? Let us discuss that. There are two sources, right? Let's imagine the sources like this, very close to each other. This is the source S1, this is the source S2. The distance between them is small d. Okay. There's a screen far away from the sources. Now we are looking at a downscaled version of that diagram. So this is the perpendicular bisector. We call this as point O. Okay. O is equidistant from S1 and S2. As you go away from O, the distance from S1 and distance from S2 will change. So Isha, you visualize and tell me, as you keep going away from O, let's call this point as A, this point as B, this point as C, and so on. The path difference will keep on changing. Keep going away from the point O. What is the maximum path difference that you can have between the waves arriving at points from S1 and S2? At each point from S1 and S2. What is the maximum possible path difference that you can have, or with which the waves can arrive at these points?
So x1 minus x2.
No, x1 minus x2 is the formula for path difference. Okay, where x1 is the distance from S1 and x2 is the distance from S2. If you take the point O, x1 and x2 will be equal. Then the path difference will become 0. So for point O, x1 minus x2 is 0. For point P, there will be some non-zero value of x1 minus x2. For point Q, which is beyond, which is above point P, okay, then the difference x1 minus x2 or x2 minus x1 will be much greater. So as you go away from the point O, that x1 minus x2 or x2 minus x1 value will keep increasing. I'm asking you what maximum value can it increase to? As you keep going away from O, what is the maximum possible path difference that can be seen? Okay, simple visualization. From S1, you imagine one wave arriving at A, and from S2, you imagine one wave arriving at A. Obviously, the distances are different. Okay, so some path difference will be there. Next, from S1, you take one wave arriving at B. I'll just change the color for you to be able to visualize. And from S2, you assume or you consider one wave arriving at B. The difference between these two distances will be different from the difference with which they arrive at A. So at A, you will have one path difference. At B, you will have another path difference. Now you take two waves arriving at C from S1 and S2, you'll have another path difference with which they arrive there. Okay. Like that, you keep going away from the point O. Then if you scale down this diagram much more, the two sources, you assume they are like this S1 and S2, separated by a distance D. And let's say the screen is here. Okay. You take a point very far away on the screen. And to that point, you imagine one wave going from S1 and another wave going from S2. It is clear that these two waves travel almost parallel to each other. Yes or no?
Yes, sir.
Okay. So if you keep going to farther and farther points on the screen, the wave arriving at that point from S1 and the wave arriving at that point from S2 become parallel. The only difference is the extra distance. Okay. And the extra distance now tends to become D, the actual distance between the sources. Yes or no?
Yes, sir.
Okay. So if you go to a faraway point on the screen, the path difference, delta x, with which the waves arrive there, tends to become distance between the sources. So that is the maximum possible path difference. Fine. The waves arriving at the point O, which is on their perpendicular bisector, there the path difference is 0. At infinite distance on the screen, on that flat screen, the path difference is D. Then anywhere in between, okay, from here to here, the path difference, okay, let me take it in the other direction. As you go away from the perpendicular bisector point on the screen, the path difference increases. And it increases to a maximum value of distance D between the sources. Path difference can never be more than that. Is it clear?
Yes, sir.
Okay. Fine. Now assume small d, that is the distance between the two sources, is greater than a small number of wavelengths, maybe greater than 5 lambda or between 5 lambda, 6 lambda, something like that. Okay. Usually that is how it is taken. Okay. Let's say the distance d is a few wavelengths. Then you can expect a path difference also up to a few wavelengths, because the maximum path difference you can expect is d, not more than that. So as you go away from the point O on the screen, the path difference increases. Then you will definitely, like as you keep going away from the point O on the screen, you will definitely come across one point, let's call it A, at which the waves arrive with a path difference of half wavelength. It's possible, no? As you keep going away from O, definitely the path difference at one point will become lambda by 2, provided the distance between the sources is greater than that. Because maximum path difference you can have is the distance between the sources. Okay. So suppose the waves from S1 and S2 arrive at the point A with a path difference of lambda by 2. A path difference of lambda by 2 with the sources being in phase corresponds to a phase difference of, if you substitute here, Let's write this formula there, delta x by lambda into 2 pi. Sources are in phase with each other. So the general formula for path difference, the general formula for phase difference on the screen at a point on the screen will be path difference divided by lambda into 2 pi. Okay, remember this is only when the sources are in phase with each other. Let's use this. So at point A, the path difference is lambda by 2. So Isha, tell me, what is the phase difference with which they arrive at point A?
So pi.
Pi. Okay. Phase difference is pi. And a phase difference pi means what kind of interference? Constructive, destructive, or neither?
Constructive.
No, pi is half cycle, no? So the waves arrive there with a difference of half cycle, means when one crest arrives there, the other one's trough will arrive there. They are doing the exact opposite things. It's destructive interference. Odd multiples of pi correspond to destructive interference, okay? So you will see a minimum there. Minimum of what? Minimum of intensity. Okay, because in constructive interference, effective amplitude of the combined wave becomes A1 plus A2, and the intensity will be the highest. If destructive interference happens between two waves having amplitudes A1, A2, then the effective amplitude becomes A1 minus A2. In that case, you will have the least possible intensity. Okay, we call it a minimum. And if the sources have equal intensities, okay, suppose the brightness of S1 is equal to the brightness of S2, that means their amplitudes are equal, A1 and A2 are equal, then A1 minus A2 becomes 0. Then you will see a completely dark spot at the point A. You will not see any light on the screen at that point. Okay, it will be black. Provided the experiment is conducted in a dark room, you will see no color on the screen at that point. Okay, in fact, this pattern, if you want to see, the experiment will be conducted in a dark room only. Okay, almost dark. Fine. Now keep going away from the point O on the screen. Then you will definitely come across one point, let's call it B, at which the waves arrive with a path difference of one complete wavelength. Okay, we have assumed the distance between the sources is a few wavelengths. Okay, that's the maximum path difference, a few wavelengths. So one wavelength is definitely possible, path difference. And if path difference is one wavelength, tell me, what is the phase difference with which they arrive on the screen?
2 pi.
2 pi. And what kind of interference does it correspond to?
Constructive.
Constructive. Phase difference of 2 pi is a difference of one complete cycle. Okay, so if one crest is arriving, the other one's crest will arrive there. And if constructive interference happens, you will see a maximum of intensity appearing at that point. So you will again see a bright spot on the screen there. If the sources are orange colored, you will see a bright orange spot there. Okay, and keep going away. You will come across another point, let's call it C, where the path difference will be maybe 3 lambda by 2. Path difference gradually increases as you go away from the central point. And if it is 3 lambda by 2, the phase difference will be 3 pi this time. Odd multiple of pi, destructive interference, corresponds to a minimum. You'll again see a dark spot there. It will be completely dark if the sources have the same intensity. Then they'll cancel exactly. Okay. If the sources don't have same intensity, then you will see the minimum possible intensity at point C. It won't be completely dark. So that's why we call it minima. We don't actually call it a dark spot. We call it minima. So as you move away from the point O, you see a pattern like this. Dark, bright, dark. Again, after C, you keep moving away on the screen, okay, to the point D, where the path difference is 2 wavelengths. If path difference is 2 wavelengths, phase difference will be 4 pi. Even multiple of pi, you will get a maximum. You will again see a bright spot. Okay. So as you keep going away, the path difference keeps increasing and you will see a series of spots like this. In fact, we have visualized the screen as a straight line. Okay, the screen is actually a sheet perpendicular to your device screen. Okay, you have to imagine a sheet of paper, okay, or a white sheet perpendicular to your device's screen. Then on that white sheet, what you will see are bands, lines, okay, of varying brightness. You will see one bright band. Gradually, the brightness decreases. You will see a dark band. Gradually, brightness increases. You will see a bright band. Okay, I'll show you a photo of that pattern. Just a moment. Pattern you see will roughly be like this. Okay, this is not an actual photo. This is also a diagram itself, but it will look like this. Okay, so this is the point O, where the brightness is maximum. Then this is the point A, where it is completely dark. Then again, this is the point B, where there is maximum occurring. Then this is the point C, where there is a minimum. Then this is the point D, where there is again a maximum. You'll see a pattern like this, okay, on the screen. The same pattern will be observed on the lower side also, lower side of the point O. Now, what are you expected to be able to do in this situation? Like in exams, what questions do they ask? You should be able to find out at what distance, okay, you can find these bright and dark bands. Okay, that distance you should be able to find out. And you should also be able to find out at what angle you are expected to see those bright and dark spots, okay, or bright and dark bands. So their linear positions and angular positions you should be able to find out. That is one thing. And you should be able to tell what is the gap between two successive bright spots, okay, or two successive dark spots. That is something we call as fringe width. Okay, see the bands that you see here on the screen, they're called fringes. This complete space from, okay, A is one dark spot. Below the point O also you'll have a minimum. From minimum to minimum, okay, or the space between two successive minima, this space is called a fringe. Okay, or that band is called a fringe. This is another fringe. Okay, minimum to minimum. Again, this is another fringe. So you'll have many fringes like this. So you should be able to tell what is the fringe width. Okay, and whether it is same for all fringes or not, on what factors that fringe width depends and all. Okay, so to be able to express these distances, there is a small mathematical idea that we need to use. Let us discuss that. Okay. Consider the sources S1, S2 separated by a distance small d, and the distance between the sources and the screen is capital D. Let's take a random point P on the screen. Now from S1, there will be one wave arriving at the point P. And from S2, there will be one wave arriving at point P. Exactly one wave will arrive from each source because the sources we considered are point sources. A point source can send only one wave in each direction. Okay, they send waves in all directions, but in every direction only one wave will be sent. Okay, so one wave from S1 and one wave from S2 arrive at point P. Now what do we want? Let's go back to the pattern. Now it's a pattern of bright and dark fringes. Okay, bright and dark bands. We need to be able to find out where the nth bright band will form or the nth dark band will form. Okay, so we need to find out this height y or this angle theta. In terms of what? In terms of the path difference with which the waves arrive there. Okay, because based on the path difference only, we'll know whether it's a bright spot or a dark spot. And based on that, we have to find out the distance or the angle. Okay, so we need to relate the angle theta and the distance y to the path difference delta x with which the waves arrive there. Okay, Now, practically, if you see, suppose you want to know where the first dark spot forms. Okay. The distance, fine, let me put it this way. Okay. Let's see what happens. From S1, let's say the distance traveled by the wave is x1, and from S2, the distance traveled by the wave is x2. So they arrive there with a certain path difference. Now, based on path difference, you want to find out the angle of the point P and the height of this point P. Height of the point P from O, let's call it as y. And the angle of the point P, angle will be taken from midpoint of the sources. It's called its angular position. Let's call it theta. Right. Now what we want to do is express theta and y in terms of delta x. Now the point P compared to the distance between the sources is quite far. Okay. So actually what happens when we perform this experiment, capital D will be much greater than small d. Why it will be much greater also you'll understand. Okay. Capital D is much greater than small d. Then in that case, okay, this is a general mathematical idea. If you have a point P which is far away from 2 points S1 and S2, and you connect S1 to that point and S2 to that point, the connecting lines are of different distances, then the extra distance traveled by one line compared to the other, or the extra distance traveled by one wave compared to the other, can be found out like this. You just draw a perpendicular from S1 onto the wave traveling from S2. You draw a perpendicular like this. Okay. Then this itself, this distance from S2 to the foot of perpendicular is the extra distance that is traveled by the wave from S2 compared to the wave from S1. Are you able to visualize this, how that is the extra distance?
Yes, sir.
Okay. Next, suppose P comes down to O. If P comes down to O, that white line that we have drawn becomes like this. Okay, it becomes horizontal. And the orange line that we have drawn, that from S1 to the foot of perpendicular, it becomes like this. Okay. The white line will be along the x-axis, orange line will be along the y-axis. Now the white line and orange line are perpendicular to each other. So if you rotate the white line by an angle theta, the orange line also will rotate by the same angle theta. Are you able to visualize this?
Yes, sir.
Okay. So let us erase these. Fine. Therefore, in the small right angle triangle that forms here, one angle is theta. The hypotenuse is small d, the distance between the sources. And the distance we are looking to find out is delta x. We're trying to find out is delta x. Okay. You can use simple trigonometry to relate these. Doing that, we get for theta, delta x is the opposite side. Small d is the hypotenuse. Therefore, sine theta becomes opposite delta x divided by adjacent. That's all. Okay. Now see, the distance d is kept a few wavelengths. Now, wavelengths of what are we talking about? Wavelengths of visible light is what we are talking about, because we want to see the interference pattern on the screen. The sources should be producing visible light. Isha, can you tell me what is the range of wavelengths of visible light? Range of wavelengths of visible light in the electromagnetic spectrum. Okay. Violet has a wavelength of 400 nanometers. Red has a wavelength of approximately 700 nanometers. Now you practically tell me, if you draw two separate dots on paper, what minimum distance can you maintain between them? You want to know that you want to clearly see that they are two separate dots. At what minimum distance can you draw two separate dots? Imagine yourself putting two dots as close as possible on paper. At what distance can you put? It will be in millimeters. Okay, maybe 1 millimeter or so. Okay, you can manage to put two dots at a distance of 1 millimeter. You can bring them slightly closer also, but it will be maybe a fraction, a small fraction of the millimeter. Okay.
Yes.
The wavelengths here are in nanometers, 400 nanometers. That's like 400 into 10 power minus 9 meters. If you convert it to millimeters also, it is 400 into 10 power minus 6 millimeters. Okay, that is 4 into 10 power minus 4 mm for violet light. For red light, it is 7 into 10 power minus 4 mm. Now, if you want to practically do this experiments and see the interference pattern, you will need two sources and you will have to bring the sources very close to each other. Okay. But how close can you bring? Millimeters? Practically, it's not possible to bring them even further closer than that. Even if you keep the distance between the two sources as 1 millimeter, the wavelength of visible light is about 10 power minus 4 millimeters. So even if you maintain a distance of 1 mm, you will get around 10,000 wavelengths within the distance d. You can't practically maintain 4 or 5 wavelengths. Okay, theoretically you can take, practically it's not possible. Okay, so even if you keep a distance of just 1 mm between the two sources while conducting this experiment, the number of wavelengths will be in 10,000s. Okay. Now what is your expectation, or what does Young want to do? He wants to see this interference pattern on the screen. If light is a wave, it should produce a pattern like this. Now, how will it produce a pattern? If it undergoes constructive and destructive interference alternately. To undergo constructive interference at the first point, okay, A, the path difference has to be lambda by 2, that's all. So path difference, you want it to be, okay, dark band. If you want a dark band, the path difference is lambda by 2, destructive interference, okay, lambda by 2. So that is 0.5 wavelengths. Whereas small d is 10,000 wavelengths. Is the ratio very small or not? Okay, the path difference expected is a fraction of wavelength. Actual distance between the sources is about 10,000 times the wavelength. So delta x by d is a very small number. Okay, and if delta x by d is a very, very small number like this, about 1 in 10,000, 1 by 10,000, that means the angles at which you are expecting, at which you should expect to see these bright and dark bands should also be very small angles. Okay, only then the sine value will be so small. And for very small angle, sine of the angle is equal to the angle itself. Okay, therefore, since the bands are expected to form at very small angles, theta is a very small angle. And because theta is small angle, sine theta, which we derived as delta x by d, is approximately equal to theta, and it's approximately equal to tan theta also. Okay, for such small angles, sine, tan, and the angle itself will all be equal. Okay. Just a little bit, in 2 minutes we'll finish this. So what did we just find out? We found out the angular position in terms of delta x. Using this, you can tell the angle at which dark bands and bright bands will form. The other thing we wanted to find out is the linear position y. Okay. Now you look at this big triangle, big right angle triangle. In this big right angle triangle, for the angle theta, y is the opposite side and d, capital D, is the adjacent side. Opposite and adjacent are related by tan. Tan theta is y by capital D. Okay. And tan theta is approximately theta itself, which is delta x divided by small d. Therefore, y is equal to delta x capital D divided by small d. We got a formula for the distance at which a particular path difference can be observed. Y is equal to delta x capital D by small d. So using this formula for theta, you can tell the angular position of dark bands and bright bands. Using this formula of y, you can tell the linear position of dark bands and bright bands. Okay. And we'll work on this in the next class. We'll derive general formulas for nth maxima, nth minima, fringe width, how the fringe width can change, how this experiment is actually conducted. All those things we'll discuss in the next class.
Yes, sir.
Fine. Thank you. We'll continue in the next class.
Thank you, sir.